spelled Joshabraham. Yeah. And organic chemistry. Gotta look into organic chemistry. Wait. Let's take a different approach today, because I still haven't figured out how to I learn this. So could question number one: IUPAC naming, assigning absolute configurations, interpret interpreting line angle structures, understanding chirality. Second question: structure drawing from nomenclature. Hmm. Question number three: reaction mechanism and stereochemistry. Question number four: completing reaction schemes. Application of standard organic reaction. Question number five: predicting reaction mechanism and products. Completion between substitution and elimination react mechanisms. Predicting the major product based on substrate. Understanding factors like steric hindrance. Okay. Question number seven: combined spectroscopy. You missed question number six? Oh. Functional group and natural product analysis. Combined spectroscopy and structure elucidation. This is a comprehensive problem integrating using molecular formulas and reaction sequence to deduce carbon skeletons and functional group. Infrared spectroscopy identifying functional groups from characteristics absorption. Nuclear magnetic resonance NMR spectroscopy H1 NMR used in chemical shift interpretation integration. I still don't understand. How is this? Carbon C13 NMR using chemical shift to determine carbon environments, distinguishing alkane, alkene, carbonyl carbons. Correlation, combining all spectral data to propose a unique structure for each unknown A through F. Carbohydrate chemistry, drawing Fisher projections for L sugars, understanding D-L nomenclature, knowing systematic names, aldopentose, aldohexose, explaining mutal rotations, the equilibrium between anomeric alpha and beta forms in open chain and cyclic structure. Let me drink this. Why do I feel sleepy after I ate? All the meals I have are same. How do I get rid of it? Oh, okay. Yeah, write down caffeine, and within 30 minutes, we're gonna do the push ups. Oh. Okay. Reaction mechanisms and selectivity. Not fully shown but implied topics, drawing mechanism for given reactions and explaining the observed selectivity. Example, regio selectivity, stereo selectivity, amino acid chemistry, and pKa analysis. Understanding the pKa value of amino acid functional groups, carboxylic acid, amine, side chain, explaining how modifying functional groups, example esterification, amidation, dramatically affects pKa values due to changes in inductive effects, resonance, and overall charge of the molecule. 12th question. 7. There's no 8. Oh, yeah. Carbohydrate chemistry, reaction mechanisms, nucleophilic acryl acyl substitution. Mm-hmm. Mm-hmm. I think I could do the exercise. That could help me. Uh, so I just exercise sheets. Just a minute, people. I'm sorry I had to mute because I was in the middle of a call. I respect let's
In this video, we're going to go over some common organic chemistry reactions that you'll need if you're studying for your final exam. So let's begin. Let's say if we have one butene, and let's react it with hydrobromic acid. So what's going to be the major product in this reaction? The alkene is a nucleophile, and it's going to react with the electrophile, which is the acid. So it's going to acquire the hydrogen
addition
and
reaction.
expel the bromide ion. Now the hydrogen is going to go on the primary carbon of the double bond. And the reason why that happens is so that we can put a positive charge on a secondary carbon. You don't want to put the positive charge on a primary carbon. Secondary carbons, or rather secondary carbocations, are more stable than primary carbocations. And that's why it works this way. If we were to put the hydrogen on the secondary carbon, we would get an unstable primary carbocation. And so that's not going to happen. In the last step, the bromide ion is going to attack the carbocation. It could attack it from the front or from the back, giving us a racemic mixture of products. So we can draw the two products like this. We could put the bromine group in the front, that is on the wedge or on the dash. So on the dash, it's going into the page. On the wedge, it's coming out of the page. So we get a racemic mixture of two products, or two stereoisomers.
Oh wait, my tap is running. It's not running as a whole, but it's just dropping, drop.
Now let's say if we have this alkene, what's going to be the major product if we react it with hydrobromic acid? And let's compare that with hydrobromic acid and peroxides. So this is an organic peroxide. Or if you see H2O2, it will have the same effect. Now, HBr without peroxides occurs with In this video, we're going to focus on IR spectroscopy, specifically how to use it to identify functional groups in organic molecules. So let's compare the carboxylic acid with an alcohol. When you have a carboxylic acid, you're going to have a very strong, very broad OH stretch. This OH stretch, it shows up at a signal between 2,500 and 3,300 centimeters to the minus 1, which is a type of wave number. Now, the carboxylic acid also has a very strong CO stretch. And the CO stretch, it shows up at a signal of 1,700 wave numbers. Now, you may want to write these numbers down because you'll need it in order to identify these functional groups in IR spectrums. Now, the alcohol, it only has the OH group. So it has a strong absorption around 3,200 to 3,600. So that's the OH stretch of the alcohol group. Now let's move on to our next one. What's the OH stretch of the alcohol group?
Let's take IR spectroscopy.
Now let's move on to our next two molecules, the aldehyde and the ketone functional groups. Both molecules contain the carbonyl functional group.
Okay. Let me draw the aldehyde and ketone. Yep, they both have.
And the CO stretch of these two functional groups is very similar to a carboxylic acid. It's around 1700. Now, the distinguishing feature between an aldehyde and a ketone is the CH stretch of the aldehyde. This signal here is the alkane CH stretch, which typically shows up for almost all organic molecules that has a CH functional group, and that's around 2900. So you'll see that for the ketone as well. But this part here, this identifies the aldehyde over the ketone. So the aldehyde will have a signal of around 2700 centimeters to the minus 1. So that is the aldehyde CH stretch. So that corresponds to that part of the aldehyde functional group. So that's how you can distinguish an aldehyde from a ketone, is the presence of this signal, the aldehyde CH stretch. Now let's compare the ester and the ether. The ester functional group has a carbonyl CO stretch. The of the
2700. Though this one is 29. For the ketone, there's no such thing.
The aldehyde CH stretch. Now let's compare the ester and the ether.
Okay, ester. Ether.
The ester functional group has a carbonyl CO stretch of around 1700. Very similar to aldehydes and ketones. The ether, it doesn't have the carbonyl CO stretch, but it does have a single bond CO stretch, and that is between 1000 and 1150. So something that you want to take into mind is that double bonds have higher wave numbers than single bonds. The C double bond O stretch absorbs at a higher energy than the CO stretch of an ether. And triple bonds have even higher wave numbers than double bonds. We'll talk more about that later in this video. For now, you want to take into account the type of carbon that is attached to the oxygen. That is, this is an sp3 carbon. Here, we have an sp2 carbon. So therefore, the CO stretch is going to be different. It's going to be higher. It's going to be between 1200 to 1300. And the reason for that is the resonance that can form here. So let's take this lone pair, let's form a pi bond, and let's break this pi bond. And now let's draw the resonance structure of the ester. And let's add the corresponding lone pairs. So we could see that the sp2 CO stretch of the ester has more double bond character than the
has more. Due to the resonance, okay.
3 CO stretch of the ether due to resonance. And why is that important? Well, as we've established, a double bond CO stretch has a higher wave number than a single bond CO stretch. So a CO stretch with more double bond character is going to have a higher wave number than the CO stretch with more single bond character.
Imagine being able to build anything. Just
Now we do have an sp3 carbon attached to the ester. So therefore, we're going to have this signal as well for the ester on the left. We're going to have two CO stretch, an sp2 CO stretch and an sp3 CO stretch. But the ether, it only has the sp3 CO stretch. And so that's how you could distinguish between an ester and an ether. The first characteristic is the carbonyl functional group. That alone is enough to distinguish it. But the second thing is the presence of the sp2 CO stretch versus the sp3 CO stretch. Now let's talk about primary and secondary amines before we go into amides. Now the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak with a signal.
Wait, the amine primary. Primary amine.
Between 3300 and 3500. Now the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the amine, the primary amine, from a secondary amine. Now the amide, it does have the carbonyl functional group. And so we're going to have a CO stretch very close to 1700. And we also have the NH2 group, so we're going to get this signal as well, between 3300 and 3500. So to distinguish an amide from an amine, you need to look for the presence of the carbonyl functional group. And to distinguish a primary amine from a secondary amine,
Yeah, carb C double bond O, and in amine 300 to 3500. The other one is 1700 due to sp3 hybridized.
look for the double peak in the primary amine
that's for different.
and a single peak in the secondary amine. Now let's talk about alkanes, alkenes, and alkynes.
Dude, how does these get here?
The alkane CH stretch
Alkane.
it has a signal of around 2900, which we talked about earlier. The alkene, C double bond C, that signal, it's a weak to medium signal, which shows up around 1660. Now the C triple bond C of an alkyne functional group, that signal is also a weak signal, and it shows up around 2100 to 2200 wave numbers. Now the next thing we need to talk about is the CH stretch of an alkene and an alkyne. So the double bond CH stretch of an alkene, it shows up around 3000 to 3100. So relative to the alkane CH stretch, it's going to be slightly to the left of it. So here is the alkene CH stretch close to 3100. Now let's say if you have a terminal alkyne, and so you're going to have the alkyne CH stretch. This signal is even further to the left of around 3300. And so here is the alkane CH stretch, and then here would be the alkyne CH stretch. So this helps you to distinguish an internal alkyne from a terminal alkyne. And to distinguish an alkene from an alkyne, you could simply look at these two numbers. So let's talk about the effect of hybridization on a wave number. So here we have an sp3 CH stretch. This is an sp2 CH stretch. And here we have an sp CH stretch. So notice that as the S character increases, the wave number increases. The sp CH...
Wait, the SP, SP2, SP3, the first one.
It composed of 50% S, 50% P. This is 25% S, 75% P. So as the S character increases, the wave number of the CH stretch goes up. Now, going back to alkanes, there's two other signals that you want to be familiar with. The first one is a CH3 bend.
Wait. I've written this in the opposite way.
It's a signal of 1365 to 1385. And then the other one, it can vary between a CH bend, a CH2 bend, or a CH3 bend. And that can vary between 1400 and 1450. Now let's talk about the relationship between
you
atomic
can't just
mass.
skip that, bro.
Now, vary between 1400 and 1450.
CH3 band 365 to 1385 centimeters. What's the difference? I don't get it.
Now let's talk about the relationship between atomic mass and wave number. As the atomic mass goes up,
Atomic mass and the wave number.
the wave number goes down. So going from hydrogen all the way to bromine, we can see that the atomic mass is going up. But looking at the wave numbers, it decreases from 2900 centimeters to the minus 1 to an average of 550. And so there's an inverse relationship between atomic mass and the wave number at which a bond absorbs.
Wait, let me just write this up.
radiation. Now, the next relationship that we need to consider is the one between bond strength and wave number. As the strength of a
Bond strength and wave number. Carbon-carbon single bond. Carbon-carbon double bond, 1660. Carbon-carbon triple bond, 2200. Carbon-nitrogen. 2200 centimeters per centimeter, 1650, 2200. That's almost same for carbon nitrogen and carbon oxygen, double, single. Thousand, 2300, 1700.
the wave number goes up. We know that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. Thus, triple bonds will have a higher wave number than single bonds. We can see that in the case of alkynes relative to alkanes, in the case of nitriles versus amines, and carbonyls versus a C single bond O stretch. And it makes sense because more energy is required to stretch a triple bond compared to a single bond, because it's harder to pull 3 bonds than 1. And since wave number and energy are directly related, triple bonds will show up at a higher wave number in the IR spectrum. So that's another thing you want to take into account when dealing with IR spectroscopy. As the bond strength goes up, the wave number goes up. Now, another topic that we need to consider is conjugation. So here we have a ketone that is not part of a conjugated system. And it's going to absorb IR energy slightly higher than 1700. So this will be around 1720. Now, for the conjugated ketone, it's going to absorb IR energy lower wave number. That is, in this case, around 1680. So make sure you understand that. Conjugated carbonyl groups, they will absorb IR energy at a lower wave number. Now, the same is true for the double bond of an alkane.
Wait, higher.
this is a non-conjugated system, and so this alkene will absorb around 1650, 1660 in that area. Here we have a conjugated alkene, and so the absorption is going to be less. This one is going to be around 1600.
Interesting. I did write a lot of stuff just within this 15-minute video.
So conjugated alkenes, they absorb IR energy at a lower wave number than regular alkenes. So remember, conjugation can reduce the wave number for ketones and alkenes. Now, it helps to remember something if you understand a reason. Remember, we said that double bonds absorb energy at a higher wave number than single bonds. Let's look at the conjugated ketone. If we draw the resonance structure, we can put a single bond on that ketone. Let me color code this. And now we'll have a positive charge here. So looking at the double bond of the conjugated ketone, and let's compare it to the double bond of the regular ketone. Which one has more double bond character? The answer is this one. This one has more double bond character because it can't become a single bond through resonance. The conjugated ketone, it can become a single bond through resonance, so it has more single bond character. And now let's think about this. We said that double bonds have a higher wave number than single bonds. So because this ketone has more double bond character, it makes sense why it would have a higher wave number than the ketone with less double bond character. So as we've considered before, as the bond strength goes up, the wave number goes up. Double bonds have a higher wave number than single bonds. So that's basically it for this video. I wanted to give you a basic introduction into IR spectroscopy. Now, I'm going to be posting another video that has a few practice problems where you can apply the information that you just learned. So when you're ready, you can just go to the YouTube search bar, type in IR spectroscopy, practice problems, and then just type in organic chemistry tutor. It should come up.
Damn, that's there.
Auf Vinted wird alles wieder neu.
Video, we're going to work on a few practice problems related to IR spectroscopy. Now, I did create another video on IR spectroscopy basic introduction. I recommend that you watch that first before trying these problems, if you haven't watched it already. So let's begin. Given this IR spectrum, which of the following
Oh shit. Gotta draw this. Okay, so these are the problems, and we got a 3000. I forgot to what is the 3000 it for the carbon oxygen double bond. Yeah, I think that's for the 3000. Now we got 1700. Oh, that's the carbon oxygen double bond. Okay, so 3000. What's the 3000? Carbon hydrogen bond. Okay, this one.
Molecules would best correspond to this graph. So one of the first things we could see is that we have a carbonyl CO stretch
Yeah.
near 1600. Now, all of the molecules that we have in our answer choices contain the carbonyl functional group. So that really doesn't help us. Now, we do have a very strong, very broad OH stretch
Not an OH.
between, looks like 2700 to 3300. So this indicates an OH functional group, which means we could eliminate answer choice B and answer choice C, which don't have it. So when you have the carbonyl stretch and the OH stretch combined, that's a good indication that you have a carboxylic acid. So right now, we're between choices A and D.
Oh, wait.
Between choice A and D is the presence of the triple bond. Now, it's important to know that the C triple bond C stretch occurs at 2200. We don't have any signal at 2200. Therefore, we could eliminate answer choice D.
Whoa, wait.
So C triple bond C stretch occurs at 2200. We don't have any signal.
C triple bond C.
At 2200. Therefore, we could eliminate answer choice D. So we could say that this particular graph corresponds to answer choice A. Now let's work on our second problem.
Wait. Shanda. Yo, not gonna lie. I'm on the stream right now. Yeah.
Which of the
That's around 500, 1000, 500, 2000, 1000.
Molecules corresponds to the IR spectrum that we see on the screen. Is it A, B, C, or D? By the way, for each of these problems, feel free to pause the video and work on it. And once you have your answer, just play the video to see if it's correct. So the first thing that we can easily
We have
identify
3000,
is
so
the
OH.
presence of the carbonyl functional group. That is the CO stretch as 1700. And for all of the answers, we either have an aldehyde or a ketone.
Yep.
Now, what else can we identify in this graph?
Alcohol, no.
Well, we do have our alkane CH stretch, which is present in every molecule.
Okay, now that's CH.
But note.
Wait. So the difference, okay. If it's a broader one, then it's alcohol. If it's shorter, narrow, it's CH, okay.
We have a signal here around 2700. This is the aldehyde CH stretch. So we know we don't have an ester or a ketone or anything like that. We have an aldehyde. Thus, we can eliminate answer choice A, which is the ketone, and D, that's also a ketone. So only answer choice B and C have the aldehyde functional group. So we're between those two answer choices now. Now, what else can we see? Answer choice B and C have the aldehyde.
That's the aldehyde.
Group. So we're between those two answer choices now. Now, what else can we see? Well, for one thing, we don't have a very broad OH signal. So that would eliminate answer choice C because that has an alcohol. We don't see that OH stretch. What we do see is a C double bond C stretch roughly around 1600. So this is it right here. And we do see the alkene double bond CH stretch around 3100. So this tells us that we have an alkene with a hydrogen on.
That's a double bond C, double bond C. Alkene.
So that would correspond to answer choice B. So answer choice B represents the molecule that best corresponds to this graph. Now let's move on to number 3.
1000, 1500, about 2000, 3000.
Identify the molecule that corresponds to this IR spectrum. So what do we see here? Looking at our answer choices, we have either an alkane.
Oh, wait, I didn't
an
complete the
alkene.
question. Wait. Option A, we have an alkyne. Option B, we have a tertiary alcohol. Option C, we have an alkene. Option D, we have another alkene.
Or an alkyne. And we have two different types of alkynes.
Yeah.
We have a terminal alkyne, where the triple bond is at the end of the molecule, and we have an internal alkyne. Well, we have our typical CH stretch at 2900, which could be found in any one of four molecules. But note that we have a signal here around 2200, and this corresponds to the C triple bond C alkyne stretch. So we do have a triple bond in this problem. We have an alkyne. So we could eliminate answer choice B and C.
Okay. Now we gotta know if it's internal or terminal.
Is it a terminal alkyne or an internal alkyne? To find that out, we do have another signal here, which is around 3300, and this corresponds to the alkyne CH stretch, which is only present for a terminal alkyne. The internal alkyne doesn't have a hydrogen to them.
Okay. Yep.
Triple bonded carbon atoms. So D is out. Therefore, answer choice A is correct. So that's how you could distinguish a terminal alkyne from an internal alkyne. It's the presence of the signal at 3300. Now let's move on to our fourth example problem.
So that's ketone. Now that's that's an ester. Because yeah, OCH3. I believe that's an ester, right? That's how esters look like. Ester, yeah, that's an ester. That's one of them. That's one of them. Aldehyde, CHO, yeah. NH2, oh, we got an amine. So we got the shorter one. The broader one is alcohol. So this is C double bond O carboxylic group, and all of them had those, and we don't have the small incisions up here, so it's not gonna be aldehyde, ester, or aldehyde. Yeah, it's not gonna be both of these. Amine, I forgot how amines look like. No, primary amine. I don't think it's. I think it's the first one, but let's see.
So looking at our answer choices, we have a ketone, an ester, an aldehyde, and an amide.
Amide.
Which of these functional groups correspond to the graph that we see on the screen?
I think it's A.
So let's identify the signals that we have.
Carboxylic.
So we have an alkane CH stretch with a signal of around 2900.
That's an alkane? Oh yeah, it's a CH. So what was the CO? That's around 2000. Okay, that's where I made the mistake.
You have a carbonyl stretch,
yeah,
or carbonyl CO stretch, with a signal at 1700. Those are the two main signals that we have. So with this information, can we identify the right answer? Well, all of the answers have a carbonyl functional group.
Yeah.
However, it helps to know what other signals should be present for the other functional groups. Looking at answer choice C, we have an aldehyde.
Yep.
We don't see the aldehyde CH stretch at 2700. Yep. So we could eliminate answer choice C. Now looking at D, we have an amide. We don't see for the NH2, which should appear as a double peak around.
Oh, okay.
To 3500. So we could eliminate answer choice D. Now looking at answer choice B, we have an ester. An ester would have a CO signal somewhere between 1000 and 1300. Oh. Since we don't have that signal, we know that we don't have an ester. By elimination, the answer has to be a ketone, because this is all that will be present for a ketone. The alkane CH stretch.
I was right,
and the
but
carbonyl CO stretch.
not for the right reasons.
So A is the correct answer choice for this problem. Now let's move on to the next problem.
Oh shit, what happened here? Hmm.
Five.
Oh, gotta draw this. What the fuck just happened over there? That should be 500. It should be 1000. Should be 1005. Oh shit. 1500. Should be 2000. What are the options? The first one is a benzene attached to an amine. Second one is a cyclic 5-carbon ring with an amine. Third one is benzene attached to amine and metal. Last one, of course, there's gonna be amine everywhere. I forgot how amine looks. So mine should be having something near 3000, and it does. So mine is there. We got triple bond. Yeah, we have double bond C, double bond C. That's triple bond. Okay, it should be around 3000, just a small incision. We do have those. Okay, so option B is not here. And amine attached to CH3. I forgot how it looked. It should be a small incision around 3300. And we don't have it. So I think option D is not part of it. Option B is not part of it. Now it's just CH. CH2 NH2. Wait. Yeah, that's the giveaway. You have primary amine. Primary amine goes around 3000 with two this, and secondary amine has a single. I'm going with option A.
So looking at our answer choices, we have an amine and we have a few benzene rings. So which of these answer choices will best correspond to the graph that we see? Is it A, B, C, or D? Well, the first thing we can notice is the signal at 33 to 3500. We have the double peak, so this corresponds to an NH2 group.
Yup.
So thus we could eliminate answer choice C because we don't have two hydrogen atoms on the nitrogen. Now, how do we distinguish between A, B, and C? Well, we do have a C double bond C signal close to 1600. So this could be an alkene or a benzene ring.
Yep.
Answer choice B doesn't have that, so we could eliminate B. Now we do have a CN signal between 1000 and 1100, but that won't help us in this problem.
What's a CN?
There is one signal that can help us to get the answer. And you might be thinking it's this signal, but this is just the double bond CH stretch, which can be found in alkenes, but also in benzene rings.
Yep.
And for answer choice A and answer choice D, we have that. So how can we distinguish between A and D? Think about what we don't have, what's usually here. What we're missing is the alkane CH stretch at 2900. Answer choice A has the alkane CH stretch right here. Answer choice D, it doesn't have the alkane CH stretch. So because we don't have that signal at 2900, we can eliminate A. Because A would have that signal at 2900, but D doesn't have the alkane CH stretch. So answer choice D is the right answer. Now let's consider number 6. So looking at our answer choices, we have an ester, an E. So answer choice D, 900, but D
What is that 29?
doesn't have the alkane CH.
Well, what does the 2900 CH? Okay.
So because we don't have that signal at 2900, we can eliminate A. Because A would have that signal at 2900, but D doesn't have the alkane CH stretch. So answer choice D is the right answer. Now let's consider number 6. So
let me draw these. 1000, 1500, 2000, 2500, 3000, 3500. And option A, we got a ketone attached to an oxygen. Oh, we got a carbon oxygen single bond. I forgot the name. We got a benzene attached to oxygen. Oh, there's more. Attached to, again, there's, and we got a ketone. It's a pure ass ketone.
Answer choices. We have an ester, an ether.
Oh, wait. We got this, what was the 3000? It's not alcohol, it's a CH, right? It's a CH bond, if I understand. Yep, that's a CH. And I think a lot of CH is there. Yeah, there's CH everywhere. Now at the 1000, CN bond. We don't have a CN, so that was different. Let me see.
Ketone. And we also have a benzene ring. Which of these would correspond to the graph that we see? Well, the first thing that we can notice is we lack the presence of the carbonyl group at 1700. So right there, we could eliminate answer choice A and answer choice D.
Oh shit, what?
The graph that we see. Well, the first thing that we can notice.
Let me see, what was the graph for carbonyl? Okay, 2000.
We lack the presence of the carbonyl group at 1700. So right there, we could eliminate answer choice A and answer choice D. Now, looking at answer choice B and C, we have two ethers and a benzene ring. Automatically, we don't have the signal at 1600, which would give us the benzene ring.
Guineo.
Don't have the signal at 16.
Yep.
Which would give us the benzene ring. Nor do we have the signal at 3100, which will give us the CH stretch of the hydrogen attached directly to the benzene ring. So we have none of those. Therefore, that tells us that we can eliminate answer choice C. Now for answer choice B, we do have the CO stretch. This is the sp3 CO stretch between 1000 and 1150. So that would correspond to answer choice B. Answer choice A, it has the sp3 CO stretch, but what we lack is the sp2 CO stretch. This sp2 CO stretch would show up at a signal between 1200 and 1300, but we don't have that. Nor do we carbon short. But what we lack is the sp2 CO stretch. this sp2 CO stretch would show up at a signal between 1200 and it has the sp3 CO stretch, but what we lack is the sp2 CO stretch. This sp2 CO stretch would show up at a signal between 1200 and 1300, but we don't have. Nor do we have the carbonyl stretch at 1700. So we can completely eliminate answer choice A. So only answer choice B would make sense. So that's how you could easily identify an ether.
Okay,
Using the
those
presence
are
of-
now. Can I do this? Following spectra is the following accompanying compound. What are the peaks that you can identify in the spectrum? What is this? Is the parts per million for mass spectroscopy? Yeah, that's for mass. Okay, I guess I have to listen to mass spectroscopy. Press C.
Right. On.
In this video, we're going to focus on mass spectroscopy. So here we have mass spectrum of pentane.
Mass spectroscopy.
And just to give you a little background information on how this technology works. So basically, you would take a sample, like this one, pentane, and put it in a mass spectrometer. And what's going to happen is that sample is going to be vaporized, and then it's going to be ionized using an electron beam. Now, when it ionizes, it can fragment into radicals and cations, but only the positively charged ions will make it through the analyzer and reach the detector. And in this graph, on the y-axis, we have the relative abundance of the fragments. So this represents the quantity of the positively charged fragments that reach the detector. And on the x-axis, we have the mass to charge ratio. Now let's say if we get a methyl cation, typically the charge will be +1. So if Z is 1, then M over Z becomes the mass of the fragment. So what we want to do in this example is we want to determine what fragments will form and which of these numbers these fragments correspond to. If you understand this, then you could use this to identify which molecule corresponds to which graph. But for now, let's identify the fragment and which of these numbers these fragments correspond to. If you understand this, then you could use this to
Wait, I did not understand.
of the positively charged fragments that reach the detector.
Let's first listen.
On the
Instead of
x-axis,
it's an exam time.
we have the mass to charge ratio. Now let's say if we get a methyl cation, typically the charge will be +1. So if Z is 1, then M over Z becomes the mass of the fragment. So what we want to do in this example is we want to determine what fragments will form and which of these numbers these fragments correspond to. If you understand this, then you could use this to identify which molecule corresponds to which graph. But for now, let's identify the fragments that form in pentane if we put it in a mass spectrometer. So let's call this carbon 1, 2, 3, 4, 5. Now, if we break the C1-C2 bond, it can split up into a CH3 group and a butyl group. Now, typically, one is going to be a radical, and the other one is going to have a positive charge. Now, carbon has an atomic weight of 12, and hydrogen is about 1. So CH3 is 15, CH2 has an atomic weight of 14. And if we add up 14 plus 14 plus 15 plus another 14, this will give us 57. So 57 could correspond to this particular fragment. Now, we don't always have to get a methyl radical. We could get a methyl cation. If we do get a methyl cation, then this molecule will be a radical. So this is another possibility. But it's important to understand that only the positively charged fragments will reach the detector. And so the methyl cation could easily correspond to the peak that we see at 15. Now, what about the peak at 43? That peak is known as the base peak. It has a relative abundance of 100%. So everything is compared to the base peak. The peak at 72 is known as the parent peak, also called the M plus peak. And it turns out that it's simply the mass of the compound. If you add up 15, 14, 14, 14, and 15, this will give you the total molecular weight of pentane, which is about 72 grams per mole. And so that corresponds to the M plus peak. Now, if we break the C2-C3 bond,
Wait. Do we... No, this is parts per million. Yeah, I believe they're gonna talk about parts per million.
get these two fragments. We can get an ethyl radical or an ethyl cation, but I'm only going to focus on the cations at this point. Or we can get a propyl radical, or even a propyl cation. Now, anytime you see a CH2 group, it has a weight of 15, and the CH2 group has a weight of 14. So the ethyl cation has a weight of 29. So that corresponds to the peak that we see here. As for the propyl cation, if you add 14, 14, and 15, that will give you a total.
Wait a minute. Yeah, Big.
of 43. Or you could do 72 minus 29, and that'll give you 43. So the propylcation corresponds to the base peak. Now here's a question for you. Why is the propylcation the base peak and not the butylcation? Let's compare both of them side by side. If we break the C1, C2 bond, we could get a methylcation, and we could get a primary butylcation. Now, which situation leads to the formation of more stable fragments? In the first scenario, where we break the C2, C3 bond, notice that we have a primary ethyl cation and a primary propylcation. In the second situation, where we break the C1, C2 bond, we have a primary butylcation and a methyl carbocation. So a methyl carbocation is less stable than a primary carbocation, which means it's easier to break the C2, C3 bond as opposed to the C1, C2 bond, because this will give us more stable fragments. And that's why this is more abundant, because it's easier to break the C2, C3 bond. Now it's important to understand that both of these cations can rearrange to a more stable secondary carbocation. But the reason why this is the base peak is because it's easier to break the C2, C3 bond due to the formation of more stable carbocation fragments. This one is less stable, so it's going to be harder to form. And so that's why this corresponds to the base peak. Now let's clear away some of the stuff that we have on the board. So at this point, we've identified all the peaks. So the peak at 15 corresponds to the methyl cation. The peak at 29 corresponds to the ethyl cation. The peak at 43 corresponds to the propyl cation. And the peak at 57 corresponds to the butyl cation. At 72, it's the original compound that lost only one electron. Now what about the peak at 41? How can we get that? So starting with the propyl cation, this molecule can lose 2 hydrogen radicals. And if it does so, what's going to happen is we're going to get an allylic carbocation. And this carbocation is stabilized by resonance. And so that's why it's very abundant as well, relative to the other fragments.
What are you talking about? I don't get it. At some point I was like, no, I don't get it. Proton NMR spectroscopy. I want to know what this is. I think I did know, I do know somewhat what this is. But what is this? We are talking about question number 3 and 4. Interpreting the spectra of a, look at the left side, the broad peak. Okay. Now for NMR spectrum, page 2. Now we're at 2. Now we're at 3. Okay. Oh, it's an exercise. Okay. Oh, H1 NMR. Okay. Okay, the following spectrum is C3H8O. Predict the splitting pattern of the following molecules. An antibiotic isolated from microorganism crystallized from water and formed different crystalline salt on treatment with either acid or base. Okay, I understand. I need to do one more thing. Just need to search, please. Login. Lock in. Login, lock in. Whoa, what the? What? Thermodynamics. Introductions to genetics. I have passed that. Organic chemistry. That's the one right now. Analytical chemistry lab course. If I remember, I couldn't register for it. No. Instrumental analytical chemistry. That's for 5th semester. Courses, course search. Please choose biologische Chemie, me, and lab course in analytical chemistry. Why can't I register for this? There's no course for this. Okay. I get that. I get it. I did register for this, right? Already assigned, yes. Dude, the introductions to general chemistry, I gotta pass that. That's one of the most important things. Introductory lab course inorganic chemistry. I should be registering for inorganic. Aiden. Just a minute, people. Yeah, we're back and I'm still registering for. I did register for inorganic. That's an important one. Application mathematics for biological chemistry. Sake. I did apply for gender studies. What else? Analytical chemistry I did pass. Lab course I can do it. Lab course in general chemistry. Why can't I do that? Oh, I gotta pass the fucking exam. God damn it. Damn it, God and damn it. Damn that got it. Where is this? Physical chemistry for biological chemistry. That's 5th semester. Did I register for that? Physical chemistry, biochemical thermodynamics, physical chemistry for biological chemistry, exercises in. What? Okay, let's look at the credits. It's 6 credits. Physical chemistry has 1150. Exercises. Do we got an exercises? Yeah, we got exercises. That's the one. Exercises in physical chemistry. course is crowded. Should I take this first? I'm still into a little bit of confusion. Well, YouTube, I'm gotta end the stream. I just gotta head back to Penny to get some grocery stuff. Gotta eat, cause you gotta survive the winter, you know. And I'll be back continuing, cause we got an exam. Peace out.